So, let us start this lecture with a thought process, that is, an attitude of gratitude is the stepping stone for acquiring any humanistic virtue. And in the last lecture, we discussed about how to use the first law of thermodynamics for reacting system. It can be flow problem, it can be what you call control mass system or a control volume system, it can be applied, but we only emphasize on the control volume system. And towards the end I told that that can be applied to the control mass system, in which case the internal energy of the reactant will be equal to the internal energy of product, particularly when you are calculating the adiabatic temperature that I have told. And today we will be looking at what you call this second law of thermodynamics first today. And first let us see that what are the limitation of the first law of thermodynamics. We all know that the first law of thermodynamics has to satisfy for a process to occur, because we have seen several processes, right, and where we have applied the first law of thermodynamics. And is it sufficient for a process to occur? Suppose I say that it is first law of thermodynamics, we state that energy can be converted from one form to other. It can be neither created nor destroyed, rather it can be converted from one form to other. And basically first law of thermodynamics talks about like how the energy interaction takes place between system and surrounding. And let us take few examples to find out what are the limitation of first law of thermodynamics. We will take our usual example of hot tea in a cup, and if you look at, let us say this is a tea which is around, let us say 200 ml, of course little bit more, but if it is having temperature of something what you call 50 degrees Celsius. So, what will be amount of heat it will be having? See, I am saying this is having at 50 degrees Celsius, and this is something 200 ml, 200 ml of tea at 50 degrees Celsius. So, what will be amount of heat it will be containing in this cup? You can very easily calculate, right, that if you take the 200 ml means basically 0.2 what kg, you can say consider water instead of tea, you can consider as a water. The Cp is 4.18 kilojoule, right. So, what it will be then? 4.18 kilojoule into 0.2 into 50, that is something 41.8 what kilojoule, right. So, the amount of heat which is there with this is something 41.8 kilojoule of heat, yes or no. And now it is kept and the ambient in the where the ambient temperature is something 25 degrees Celsius, and you will allow a certain amount of time which is sufficient for this temperature T, which is from there will be some reach the equilibrium temperature with the ambient, because heat being transferred Q. So, what will be amount of heat is going out? What will be going out? Because this T will be reaching thermal equilibrium after let us say 1 hour or something like that, okay, 25 degrees Celsius, that means half of the heat energy will be going out, that is something 20 what you call 0.9 kilojoule, right. Yes or no? So, if it is going out, that means the energy from here from the cup it has gone, and what is remaining there here, it will be, this will be reduced to 20.9 kilojoule, right. Yes or no? Now, this amount is there in the surrounding, this is your surrounding, right. So, this what the first law of thermodynamics says, that heat energy has gone from the hot T to the ambient or the surrounding ambient air, and then that energy can come back to it. Is it possible? That is silent. First law of thermodynamics is not saying the energy can go from here to there and it can come from other way around, right. So, that means that we know from our common sense that we cannot really what you call heat the tea, okay, just taking the heat which is being transferred to the ambient air by itself, right. That means the whatever energy is there here, can it get back to here? It won't, it cannot be, right, it cannot be. So, that is the common sense we do, therefore, it is not really possible for the process to take in the reverse direction. That means, from what you call to the I am like from the cooler room to the tea. Okay. So, let us take a few more examples just to illustrate this point. What we will do? We will take a container which having certain amount of water, and this is our control system, I can say, that is your system boundary, right. And then we will make the pedal wheel to run, and it will be what you call the mass is being raised against gravitational field. So, that means some work is done, right, some work is being done here. As a result, if it is at 25 degrees Celsius and let us say it is going to the something 35 degrees Celsius water, tea, right, that means the work is converted basically into heat. Whether that heat, whatever the energy is there, I can get the work done. Is it possible? Because now this has converted, the work is converted into heat, right, and can I get use this heat to convert into mechanical energy or the work? Is it possible? Our common sense says certainly no, right. That means it is not possible for raising a mass by the heat interactions. Although the first law of thermodynamics won't violate, if you say that look, this heat can be converted into mechanical work, this first law of thermodynamics is not violated by this, right. So, let us take another example, that means water stored in a high rising building or any building rooftop, and it will be again released from that, and it will come down, and there at the certain height z there will be potential energy that is converted into the kinetic energy, right, and of course, at the ground level, right. And we cannot really get back this water into the tank which is placed on the rooftop again, right. So, that our common sense says that it is not possible, right. That means from these examples, right, what you can see, that process proceeds in certain direction only, right. Yes or no? I will give another example which is just crossing my mind, like so for example, you are now youth, right, maybe around something 17 or years back or 18 years back, you people are toddlers, moving around, trying to walk, trying to talk and other things, right. and after few years you become middle age, and then after many years you become old person, right. And whenever you talk with your grandparents, they will say, look, my childhood was very great, today I do not know why it is. Everybody wants to go back to his childhood, right, because that is the beautiful part of the life, what people say. So, now is it possible you can go back? Can anybody go back to the your childhood, or maybe suppose you are old to the middle age or to the youth? No, you cannot. It is one directional. Similarly, that is the thing, that means feasibility of a process basically can be determined by the second law of thermodynamics. So, for a process to proceed, that means both the first and the second law must satisfy. It is not that first law alone. That means the first law is necessary for any process to occur, but that does not mean that it is sufficient. But when you apply both the first law and second law, that means the process will be possible. So, let us before really delving into the second law of thermodynamics, we will define certain terminologies, because that is very important to get acquainted with the terminology. Of course, you will be knowing that we will be using thermal reservoir. So, what do you mean by this reservoir? Reservoir basically it will be having a large thermal capacities, right. Let me give an example of that, right. Reservoir means always we say reservoir means water reservoir, right, is not it, water reservoir. Like if there is a very big lake is there, right, and I will take maybe let us say few thousand liters from that water level will not really change. Let us say I will take something let us say 10,000 liters, but if I take a 10,000 liter from a what you call well, then the height of the water water in the well will be reduced. That means it is changing, right. And therefore, the reservoir is basically can be several things. That means the thermal reservoir which one in which no change in temperature will be taking place by the heat interactions, right. That means it will be very large amount. Let us say there is a thermal reservoir, right, let us say a combustion is taking place, and you will take some amount of heat from that which is very less. Let us say boiler, it is something megawatt. If you take some few kilowatt, there will not be any change in temperature, that, right. And the examples of reservoirs are river, lakes, ocean and atmosphere, right. These are the examples of the reservoir as I told. But this reservoir also contains a large amount of the thermal energy, if you look at, yes or no, right. Even if you take let us say ocean, it is a large amount of quantity of water, and then it is having let us say something, even if you take 25 degrees Celsius, it will be huge amount of thermal energy, right. Okay. Of course, that cannot be utilized as a source. Like we will divide this thermal reservoir into two kinds. One is a source, other is sink. That means that reservoir which supplies the heat to any system or engine, that we call it as a source, right. And sink which absorb the amount of heat, like kind of things. So, if you look at like your nowadays, you take some money or the resources from your father. Father is a source for you, and you are giving to the shops and other thing, they are the sink, right. Suppose you are buying certain items and giving to a shopkeepers or the people, then that is a sink, and your father is a basically source and you are utilizing it. So, sink which absorb the heat, that we call it as a sink. So, reservoir basically, as I told, that the source which is having a temperature T1, if you take certain amount of heat Q, this temperature will not change, right. This will remain constant, right. This will be remaining constant, temperature will not be changing of that reservoir. And similarly, the sink, if it is at certain temperature, let us say if it is 25 degrees Celsius, right. So, if it is 25 degrees Celsius, right, and if you are giving certain amount of heat, let us say it is a lake kind of things, and you are giving some amount of heat to it, So, this temperature will be not remaining, will not be changing, will be remaining constant. So, this will be right, it will not be affected by the heat interaction. Generally, the source temperature will be much higher than the sink temperature, right. So, the examples of the reservoir will be basically, as I told, there will be combustors, even nuclear reactors, and then boilers and other thing for the source, and the sink will be your lake, river, and your what you call pond, and then sea. That is why we are using the basically our environment or the air itself. So, we are giving large amount of heat into that, therefore, there is a increase in the temperature kind of thing. So, basically we will have to say that how we can convert the heat into mechanical work. So, that is by using a heat engine, and heat engine is basically a energy conversion device that takes certain amount of heat from the thermal reservoir that we call source, and then it will be giving some amount of heat to the sink and also produce certain amount of work done. So, therefore, heat engine can be defined as a cyclically operating device that receives certain amount of heat from high temperature source, that is the thermal reservoir, right, high temperature. And the example, as I told, combustor, nuclear reactor, boiler, any other things one can think of, and converts a part of this heat into mechanical work and rejects the certain amount of heat or the remaining amount of heat to low temperature, what we call it as a sink, low temperature sink. And it can be atmosphere, the sink, it can be river, it can be lake and other things. So, if you look at like there are that is the way how it has to be done, that heat engine operates. So, question is how to convert heat into mechanical work. So, what we will do, like we will have to, as I told earlier, that we will have to take certain amount of heat, that is QH, from the source, high temperature source, and this is a cyclically operating device, heat engine, and it will be certain amount of this absorbed heat from the source will be converted into work, and certain amount will be rejected to the sink. So, by this way one can really what you call convert the heat into mechanical work. So, let us take an example like in a heat engine, and this example is steam power plant. There are several kinds of heat engines, steam power plant is one of them. In this case, if you look at, this is the what you call the boiler, which is basically large amount of heat being generated, and from this the fluid will be taking certain amount of heat QH, and then it will be going to the turbine, which will be expanded, and then the work, mechanical work is being what you call obtained, and then that fluid will enter into the condenser, where it will be rejecting the heat to the cooling water, right, because cooling water will be coming and then going become hot. So, then again this fluid is basically getting into pump, and this pressure will be raised, again it will be entering into the boiler. So, if you look at this is a closed cycle, right, it is a closed, that means fluid is not going out. Therefore, if I want to analyze this, what I will have to use, whether the control volume or control mass, definitely it will be the control mass system, and this I have taken, it is your system boundary, right, this is your system boundary. Now, you keep in mind that what is happening here, here the boiler to the system boundary certain amount of heat, that is QH is entering, and the certain amount of heat is going out from the system boundary to the your cooling water, that is QL, right, and work is being produced, that is by the turbine, this is WT, and you will have to supply the work for the pump. What is the net work done then here? That will be WT minus WP is your net work done. So, what we will do, as I told, no mass is going out from the system boundary, right. So, therefore, we are using a closed system, and according to the first law of thermodynamics, the cycle integral of dq is equal to cycle integral of the dw, that is the work, and we have seen that the amount of heat which is entering into the system by the source is QH, and QL is the amount of heat is going to the sink, and is equal to the amount of work produced by the turbine, and you will have to supply the amount of work to the pump, and that is your net work done, right. And this is just you are applying the first law of thermodynamics for a cyclic process, because this steam power plant works in a cycle. And as this QL cannot be 0, right, certain amount you will have to give, therefore, the net work is always less than QH, the amount of heat which is absorbed from the source is always will be higher than the amount of work produced by the turbine, the net work. Basically, it is the turbine work minus the pump, that is the net work what you will get, because from the turbine you will have to give some amount of work to the pump to be operated. So, therefore, we will define a term to characterize how good it is, that we call it as a thermal efficiency, that is by definition, that is eta Th is equal to W net, right, divided by QH. And what is this W net? W net is nothing but your QH minus QL, that is your W net. So, QH minus QL divided by QL is equal to 1 minus QL by QH. Keep in mind that QL will be some finite, right. So, therefore, the thermal efficiency will be always less than 100%. That means, all the heat cannot be converted into the work, right. So, that is the things what we are looking at it. So, heat engine basically efficiency can never be 100%, it will be always less than 100%, right. So, is there any way we can minimize this heat which is going to the sink, heat being lost to the sink. So, in a condenser we have seen that a steam power plant, large quantities of waste heat is rejected to rivers, lakes and atmosphere. Therefore, you will find the temperature is being what you call the places being increased, and then marine life also being affected, because you are producing a large amount of putting it. Not only that, pollution also, water pollutions and other things comes into picture. And so, can we just not take the condenser out of the plant and save all the waste energy? Because it is waste. Is it possible that I can utilize those heat which is going to the condenser for some other purposes, so that I can enhance the efficiency, right? So, that is the challenge what is being done, and the people have trying to use it, but I will be not discussing about that. And but however, you cannot eliminate it, you can minimize, you can reduce it, but you cannot make it 0 QL. Why it is so? Let us look at that. We are having a gas at let us say 25 degrees Celsius to start with, right, and it has been connected, what you call, if you look at, like, it is having, I can take this as my system, right, and it will become connected with the source which is at 300 degrees Celsius, and then what will happen? Like, it will be, gas temperature will be increasing, right, and when it will increase, let us say it is going to 200 degrees Celsius, that means the work is being done, right, piston is moving up in this case. Now, right, so then after that it has reached the state 200 degrees Celsius, let us say. Of course, you can increase this further to the 300 degrees Celsius and giving certain amount of heat into the gas. But now I want to get it done, because it has reached a state where it cannot come back again unless it is. That means I will have to put into what you call, into a sink to make it cyclic, to work it continuously, right. So, what I will say, I will have to give this gas, what you call, bring a sink here and then put that sink, so that heat will be transferred, and then the piston will move back to again original state, that is what you call 50 degree Celsius, and then so that again it will go as a cycle. Otherwise, you can get the work done for a certain period of time, after that you cannot. So, it has reached a state. So, therefore, it is very important to that without heat rejection process in a condenser, the cycle cannot be completed, right. If it is not completed, you cannot really get the work in a continuous manner, you will be getting the work in a discrete manner, right. So, therefore, it is important to reject the heat. So, we can conclude every heat engine must waste certain amount of energy by transferring it to a low temperature reservoir in order to complete the cycle, even under idealized condition, right. So, therefore, it is very important that heat engine has to reject certain amount of heat to the sink. So, other examples of heat engines, of course, the piston engines like what we use in automobile, and gas turbine engine, Wankel engines, and but from a simple steam power plant, we know that a heat engine must reject certain amount of heat to low temperature sink to complete the cycle, right. So, therefore, we can say that no heat engine can convert all the heat it receives from the source into equivalent work. So, it is impossible to absorb certain amount of heat from a source thermal reservoir, and does the equivalent amount of work. So, that is basically the Kelvin's Planck statement and of the second law of thermodynamics, that we states that it is impossible for any device operating in a cycle to absorb the heat from a single thermal reservoir and produce an equivalent amount of work. That means, if you look at schematically, that is, it is impossible to have a cyclic operating device heat engine certain amount of QH and converted fully to the work, mechanical work. That means, the thermal efficiency of this heat engine can never be equal to 100%. It will be impossible to have to that kind of engine which is having 100% efficient thermal efficiency, 100% efficient thermally. That means, heat engine must exchange heat with a low temperature sink. So, let us look at refrigeration and heat pump. Basically, if you look at what we have seen, a heat engine which will be absorbing certain amount of heat from the thermal reservoir and giving certain amount of heat to the sink and doing the some amount of work. But there is another application where the heat has to be taken from the low temperature medium to the high temperature, and of course, you will have to give certain amount of work. That is, like for example, you are doing the air condition, right, and in which case the heat has to be basically taken from the low temperature medium and leaving, let us say from this room, this is the low temperature, and then it will be transferred to the surrounding, that is the ambient air which is at higher temperature, that we call it as a refrigerator. And refrigerators like heat engine has to be operated in a cyclical manner, right. It is basically a cyclic device. So, let us consider the how it operates, and what it will be doing. It will be basically taking certain amount of heat in evaporators, right, and then it will be compressed, and again in the condenser, which will be certain amount of heat has to be rejected to the high temperature surrounding. So, if you look at the surrounding will be at a high temperature, like T high temperature, and this is your T low temperatures kind of. And then it has to expand it in the throttling valve, which we have discussed in the maybe few lectures, back kind of things, that where we have found out that it is an isenthalpic process, right, and where the temperature will be reduced and then it will come back. So, if you look at this operates on the cyclic what you call way. So, working fluid will be used, and that fluid in this refrigerant cycle is known as the refrigerant. There are various kinds of refrigerants will be being used, and some of them are toxic in nature also, and it gets. So, in the household refrigerator, if you look at the freezer compartment where heat is absorbed by the refrigerant, serve as a evaporator, right, and the coils usually behind the refrigerator where heat is dissipated to the air. Of course, if you have kept the your refrigerator in the kitchen, that is the kitchen air, serve as a condenser. You might have seen that is quite hot, like of course, nowadays the people are covering it, and one has to keep this refrigerator properly, otherwise it won't function properly. Why? Because the heat has to be dissipated, right. So, let us look at that how to evaluate or its performance. For example, this is a refrigerator which is taking certain amount of the heat, that is QL, at from the cold refrigerator space, that is your basically evaporator, kind of thing at TL is a lower temperature, and then certain amount of work is being done, right, put into this, and then you will be transferring QH amount to the warm temperature, that is TH is greater than TL. That means, this temperature is basically is higher than the low temperature. Now, if you look at this is your, that means always we will have higher amount of this heat which will be extracted. So, that the temperature will be maintained at particular low temperature if we are fixed, or it will be lower. So, therefore, we will have to define a term which is known as the coefficient of performance, right, and is basically ratio of the desired output by the required input, right, that is the COP we call coefficient of performance, that is QL divided by net input work input. So, the net work input will be nothing but QH minus QL, and COP is basically QL divided by QH minus QL. If you look at, if I can divide by this, I will get the ratio basically. If I divide by QL here and this by QL, I will get 1 over QH divided by QL minus 1. So, this is the way how it will be, you can evaluate how good it is. And is it this coefficient of performance will be greater than 1 or less than 1? What it will be? We have seen the heat engine is basically always will be less than 1, right? We have seen. In this case, what it would be? What it would be, right? It will be always greater than 1, right, isn't it? And if you look at why we have not used the efficiency, thermal efficiency here for the refrigerator, why you have really divided the coefficient of performance, why? Because we have already defined, thermal efficiency cannot be greater than 1. If we will define that way, that means it will add to the confusion. So, therefore, we use a new terminology known as coefficient of performance. So, let us look at a heat pump, and heat pump is basically we use in the winter season, right, where you will have to supply the heat to your room, which will be at higher temperature as compared to the ambient will be lower temperature, right, kind of things. So, in that case it is just the application what matters, right. So, as I told, the objective of the heat pump is to supply heat QH into warmer space, and the work supplied to the heat pump is used to extract energy from the cold outdoor and carry it into the warm indoors. For example, like if you look at, this is the heat pump, and which takes the heat from the cold environment temperature, let us say in the ambient air in the winter season, QL, and then certain amount of work is done, input is given, and then it is the QH amount of heat has to be go to the warm heated space. So, if you look at, in this case, the desired what you call output is QH. In case of refrigerator, what was the desired output is the QL, just opposite. So, and let us take like an example like warm indoors will be, you can try to maintain at 20 degree Celsius, and whereas the outdoor temperature which is at 4 degree Celsius. That means, you will have to take certain amount of heat from this low temperature, let us say 5 kilojoule, then you add something 2 kilojoule of work input, then you will have to supply the amount of QH 7 kilojoules, of course. And in this case, the COP is something 3.5 kind of things. This comes, if you just do that. So, this is basically the heat pump what we call, and COP of heat pump can be defined as the ratio of desired output divided by the ratio of desired output and required input, that is QH divided by W net, and that is COP is basically QH divided by QH minus QL. So, we can say that it is 1 by Q 1 minus QL by QH. So, for the same input heat input ratio, like for the same QL by QH, whether the COP of HP will be same as that of the refrigerator or it will be different, how it can be related. Let us see that, and before that we will see that the value of the COP lower can it be lower than the unity? Certainly no, it will be higher than the unity, as I told in the refrigerant case. And what does COP HP equal to 1? It basically it says that whatever the energy, if I say this is equal to 1, right, COP is equal to 1 means what? That means the QL, right, whatever it is going, it will be from the cold temperature, it will be getting into the warm heated temperature without any work input. That is really not possible. So, you can from this one can say that COP HP is equal to COP R plus 1, you can derive that expression, right. That means which says that COP for the same ratio, the COP of refrigerator will be lower than the COP of the heat pump for the same what you call heat interaction, right, for a fixed values of QL and QH. So, keep in mind that the COP of the HP is higher, and generally the coefficient of performance of the refrigerator is being range something maybe around 2 to 3 kind of things. But if you use let us say you want to store your ice cream at a very low temperature, so that it will not melt down. So, then therefore, you will have to you will want a freezer kind of things, or you want to store the meat or fish in a low temperature, then that COP of the refrigerator is very low, it will be around something 1 to 2 kind of things. Now, when you are designing, you will have to take care like what is the application, but if you combine that both together you want to have, then you will always having a very low COP, and low COP means the cost of the things will be very high, right. So, what I am saying, this performance parameters helps to tailor your design depending on the application. So, let us consider that like your basically a engine, like heat engine kind of things, reverse heat engines, that is we say that it takes certain amount of QL from the cooler body and also gives the certain amount of heat, the same amount of heat to the hotter bodies, and which is really not possible, because no spontaneous flow of heat is possible from cooler body to the hotter body by its own, that we have seen like, and that is nothing but your Clausius statement. We say that it is impossible for any device operating in a cycle to produce no effect other than the transfer of heat from cooler body to the hotter body. If you look at Kelvin Planck statement is about basically the heat engine, and the Clausius statement is basically about the refrigeration system or the heat pump, right. So, now question arises, like we will have to see that in other words it says that it is impossible to construct a refrigerator without any external work, and COP of refrigeration is infinity, is impossible, rather always COP of refrigerator will be greater than 1. and second law of thermodynamics based on experimental evidence. Till now no experimental evidence exists to disprove this statement, right, to kind of things. So, therefore, it is there and it is similar to your first law of thermodynamics. And there might be one question coming to your mind, like is this Kelvin-Planck statement same as that of the Clausius statement, right, because one is for heat engine and other is for the your, if you look at Clausius statement is for the your refrigerator. Is it same or different? So, what we will do, we will look at it. Of course, the answer is yes, but can we prove it? What we will be doing? We will be taking a deduction route to say that it is true that both the statements are same. So, let us assume the Kelvin-Planck statement is incorrect, right. What that means? What that means, there is a heat engine, reversible heat engine that takes certain amount of heat and does the equivalent amount of work. So, that is the thing what I was telling, that the from thermal reservoir there is a heat engine which takes certain amount of heat, that is Q1, and it does the same amount of work. Hypothetically you are saying it is true. Now, let us take this, that is another reversible heat engine, that is your refrigerator, which takes certain amount of heat QL from the low temperature reservoir, thermal reservoir, and certain amount of work is done, and as a result it gives this reverse heat engine that gives the QH amount of heat to the thermal reservoir, right, that is a source. And what we will do, we can say that this basically Q L and this amount, instead of this, what we will say, we will take from here, from what you call this amount of heat is taken from here instead of this, Q1, right. It basically take this amount of heat Q1 and then it is not taking from thermal reservoir. As a result, what happens, that it gives, if I take this as my combined system or this thing, that means it takes certain amount of heat QL and it is giving the same amount of heat to the thermal reservoir at high temperature, that is called source, right. It takes from the sink QL amount of heat, this is your sink, right, and it gives to the same amount of heat to the what you call to the source. That means it violates the Clausius statement. Okay. That means what I can say, violation of Kelvin-Planck statement leads to the violation of Clausius statement. So, let us look at other way around. We will say that Clausius statement is actually violated, right. That means I will say that there is a reversible heat engine which absorb QL amount of heat and also giving the same amount of QL to the source, which is at a higher temperature than the sink. So, then what we will do, we will again consider the another heat engine which absorbs QH amount of heat and it does certain amount of work and leaves certain amount of QH, that is QL, into the sink. Now, we will combine it, right, and together, that means this amount of heat is going here, what you call QL, instead of going to this thermal reservoir, this is going to this place QL, right, and this QL, instead of going here, you give to this place, So, what will happen, the whole system says that means this system, the new system, when you combine it takes QH minus QL amount of heat from the thermal reservoir, right, and does the same amount of work, that is QH minus QL. We state that violation of Clausius statement leads to the violation of Kelvin statement. Therefore, that Clausius statement is equal to Kelvin Planck statement. So, we have seen that both the Kelvin Planck statement of the second law of thermodynamics is same as that of the Clausius statement of second law of thermodynamics. So, both are same, by deduction we have seen. So, we will stop over here and we will consider the other aspect of second law of thermodynamics in the next class.